The earlier video summarized the evidence for lateral dike propagation away from the Bárðarbunga caldera, and the GPS data and the INSA results presented in Module 2 allow modeling of the dike opening. Initial models of the diking show that the deformation data require the dike to be approximately vertical and line up with the seismicity. This formed the basis for more advanced models by Andy Hooper, shown here in this figure. The dike was fixed to be vertical, and the lateral position of the dike was fixed to coincide with the earthquake locations. The dike is modeled as a series of rectangular patches or kata dislocations, and opening and slip on each patch was estimated using a Bayesian approach. The figure shows the median of the posterior probability distribution of opening for each dike patch and relocated earthquake hypocenters as dots. Black dots are in the front of the dike and gray dots are behind the dike plane. Red stars mark the eruption sites. These results suggest that most of the magma injected into the dike is shallower than the seismicity, which mostly spans the depth range from 5 to 8 km below sea level. While magma may extend to depths greater than 9 km near the center of Bárðarbunga, towards the edge of the ice cap, where constraints from INSA and GPS are much better, significant opening is all shallower than 5 km. The total volume intruded into the dike by August 28 was about half a cubic kilometer. Some opening continued into early September, but thereafter, and for the 6 months duration of the eruption, ground deformation was focused within the Bárðarbunga caldera. The eruption was accompanied by a slow caldera collapse, a truly rare event providing a unique opportunity for better understanding the volcanic structure and processes. The collapse was extensive, as the 8 by 11 km wide caldera gradually subsided and a bowl up to 65 meters deep was formed. About 1.9 cubic kilometers of magma drained laterally along a subterranean path feeding an eruption 47 km northeast of the caldera. The map in this figure shows the total caldera subsidence in meters at the end of the collapse in February 2015, mostly based on radar profiling from an airplane. The hatched contours indicate subsidence in meters. The blue dotted line is the 1 meter subsidence contour. The panels on the left show two profiles across the subsidence as measured in June 2015, corrected for winter snow accumulation in 2014 to 2015, and corrected for modeled vertical ice flow. Since the caldera is subglacial, it was important to consider if some significant part of the change on the surface of the ice cap was due to ice flow. The conclusion in this case was that the displacement of bedrock was comparable to the ice surface change. Difference between observations and ice flow corrected surfaces was minor. Seismic activity in the caldera provides indications that the caldera faults did only start to move some days into the eruption, after significant volume of magma had flowed from beneath the caldera. Panel A in this figure shows a cumulative seismic moment release from caldera earthquakes plotted together with distribution of seismicity along the dike length, using relatively located earthquakes. For the time period when the dike progressed away from the caldera, black dots show individual earthquakes with dot size scaling with magnitude. In panel B, significant caldera earthquakes with magnitude above 4 are plotted as impulses, where the height presents magnitude and color represent location on the southern or northern rim. The 4 panels on the right show maps of northwest Vatnajökull with earthquake epicenters on separate dates: 16th August, 17th to 19th August, 20 to 22nd August, and 23rd to 25th August. The stars indicate the larger than magnitude 4 earthquakes in the caldera. These show how the seismicity was propagating away from the caldera. When sufficient volume had been withdrawn from beneath the caldera, earthquakes larger than magnitude 5 began in the caldera, in association with gradual caldera collapse. In this figure, the upper panel shows subsidence at the center of the caldera and subsidence volume evolution. The volume of the subsidence is obtained by subtracting the mapped surface from the pre-collapse surface. Exponential decay over time is suggested. This led to a development of a piston collapse model shown schematically in the lower panel. A block bounded by caldera faults subsides and exerts pressure on the underlying magma, helping driving magma out of the source. Consideration of the physics involved shows that such a model predicts exponential decay in magma flow rate as observed. The lower figure on the left shows magma flow rate constrained by caldera subsidence observed by GPS, compared with rate of volume change in caldera and the eruption rate in Holuhraun, based on mapping the volume of the lava field. A similar flow rate curve was inferred from the volcanic radiative power observations of the lava field observed by satellite, presented in Module 3 in Video 3.6. The eruption stopped before the driving pressure reached zero, as expected if the conduit becomes clogged by solidifying magma as the flow rate drops. Caldera subsidence also terminated around the end of February. This figure shows a schematic cross-section of an interpretative model together with photographs showing the Bárðarbunga caldera and the Holuhraun eruption site. The cross-section shows the caldera, a magma reservoir, a pipe-like magma flow path, and the eruption site after dike formation. The model is independent of the exact geometry of the magma flow path. It simply requires it to be somewhere within the dike complex. The inferred magma reservoir is here set at 12 km below bedrock caldera floor, based on initial suggestion from geobarometry, shown with a white arrow, and constraints from geodesy, shown with a blue arrow. It is possible that the magma ascended first along the ring fault before forming the dike above the 6 to 10 km depth. At Bárðarbunga, series of observations thus suggest melt withdrawal from a magma body beneath the caldera, slip on caldera ring faults, and transfer of magma along a 48 km long dike, which was feeding the major effusive eruption on the Holuhraun plain. Magma drained from beneath the caldera was initially emplaced in a dike and then erupted at the far end of the dike. The calculated volume change at the end of the eruption, associated with magma withdrawal from the modeled sill at about 10 km depth beneath Bárðarbunga, was about 1.9 cubic kilometers, and it was about 0.7 cubic kilometers for the dike volume, according to a study by Michel Parks and colleagues. The difference is roughly equal to the volume of the lava field produced. The dike opening mostly occurred over a period of weeks, whereas the caldera subsidence at Bárðarbunga occurred gradually over a period of 6 months, simultaneous with the 6-month-long lava flow eruption at the far end of the dike. This study and the rich observational datasets show how gradual caldera collapse may be responsible for driving out large volumes of magma in an effusive eruption that can take place far away from a collapsing caldera.